Hi everyone, today I'll be presenting the introduction part for Principal Chemical Engineering and Fluid Dynamics. So let's get to know about isopropyl alcohol first. Isopropyl alcohol is one of the most common members of the alcohol family of organic compounds, also known as isopropanol. The characteristic of isopropyl alcohol is colorless, bitter liquid commonly found in hair tonics, cleaning products, and many more. It has boiling point at 82.3 degrees Celsius and freezing point at negative 89 degrees Celsius when measured at normal conditions. Isopropanol is miscible in water, ethanol, ether, and chloroform. Now, we're moving on to the introduction for the fluid mechanics. Chemical engineering fluid mechanics combines principles from fluid dynamics, thermodynamics, and transport phenomena to analyze and understand the behavior of fluid under different conditions. This case study delves into the fluid dynamics involved in the pipeline system of an isopropyl alcohol production plant to optimize energy losses and ensure a smooth fluid flow, maximizing the utilization of resource for efficient plant operation. Reynolds experience are utilized to study incompressible flow, distinguishing between laminar and turbulent flow regimes. The Reynolds number can determine flow behavior, categorized as laminar, which is the Reynolds number is less than 2000. For turbulent, the Reynolds number is more than 4000, and transitional, the Reynolds number is in between 2000 and 4000. The calculation of Reynolds number can be done using the formula shown in the slide. Bernoulli's equation can be used if the flow of liquid in pipeline system is steady and incompressible. Bernoulli's equation relates the states at 2 points along a single streamline. In a pipeline system, external factors such as pump work, turbine work, and friction losses can also affect fluid flow. So Bernoulli's equation must be modified to account for these factors. Therefore, Bernoulli's equation can be written as shown in the slide. The total friction loss or head loss in a pipeline can be calculated by adding all the individual friction losses due to the pipe, fittings, valve, expansion, and contraction, which can be represented by the equation shown in the slide. And then for the friction factor, we can calculate depends on the flow of the water, whether it is laminar flow or turbulent flow. Okay, thank you.
So this is the flow diagram of direct hydration process for the manufacture of isopropyl alcohol. So for the left part, propylene and water are used for isopropanol production. Propylene and water were pumped, preheated and fed to a reactor under pressure of 1 atm and 80 Celsius. The reactor received 3300 mol per hour of propylene and 3300 mol per hour of water. Subsequently, the reactor output was propylene, water and isopropanol fed to the separator. The top product stream was propylene gas and was recycled. So for the right part, most of the unit process are distillation column. Benzene is added to the mixture at the entrainer. The mixture of isopropanol and water is sent to the isotropic column to isolate the isopropanol product more than 99.5% at the bottom, whereas the ternary isotropic form from the entrainer, water and a small amount of isopropanol is delivered to the top. The overheat stream is then input into the center, separating the feed into organic and aqueous phase. Subsequently, the organic phase recycled back to the distillation isotropic column, and the aqueous phase is distilled in other distillation column that separate the water at the bottom and the isopropanol water isotrope at the top, before recycling this isotrope to the distillation isotropic column.
Hi, my name is Ikmah Haril and I will be explaining about the mass balance for the non-reactive system and reactive system. Alright, so for the non-reactive system, we are choosing the purification distillation of isopropanol. This would be the assumptions. You have to take the basis of calculation of feed and what are the compounds in the feed and how much percentages of it. We are also need to know the percentage of isopropanol that is needed to be isolated, because we want the isopropanol to be pure, hence the name purification distillation. Now we are also going to assume the unrecovered isopropanol is released to the top stream, so the leftovers isopropanol would be at the top stream. And these are the independent equations that was created from specific component balance, overall general balance, and also from assumptions. 6 independent equations, 6 unknowns, degree of freedom analysis, 6 minus 6, 0. Perfect. So it's solvable. For the bottom stream, considering that 99.6% of feed IPA is released at the bottom of column, we just have to times that value with the feed IPA, which is just 70% of 5000. So we will get 3486 mole per second. And considering that bottom stream contains IPA only, so it's just 1. 3486 over 3486 is simple. For the top stream, we are going to use the equations, the independent equations early on. And from there, we can find the molar flow rate of top stream, total molar flow rate of top stream, M2, and we can also find the mole fractions, X1, Y1, and Z1. Simple. We continue with the mass balance for reactive system, which is the hydration of propylene. So these are the assumptions. We are going to take our basis of calculation, which is 3500 of propylene entering feed. Assume that it is 100% reacted. Assume excess feed water will be 32.86%, and that will be the assumptions. And from these assumptions, we can then calculate the amount of IPA that will be produced, and from there we can compare the stoichiometric coefficient to find the water in the output stream, and we can find the value of input stream for water using the excess equation. Now for the energy balance, we are going to look at the reactive system first. Firstly, we are going to state our temperature and pressure for each stream, as you can see at the flow chart. Then we are going to assume that we have zero change in kinetic energy, zero change in potential energy, and zero work done by the system. So from there, we will get that the heat loss or gain is the total is equals to the heat of reaction. Now, early on, we have gotten the value of flow rate. Now, how do we calculate the specific enthalpies for each compound? Firstly, we have to look at the phase changes, whether the phase change from gas to liquid or liquid to gas. Secondly, we have to look out for the temperature changes, such as C3H6 over here. We have the temperature change from 25 degrees Celsius to 80 degrees Celsius. We also have to look out for the pressure changes. Now, these are the three things we have to take into account in your calculations, and this will be the steps. Now, the only tricky part here will be for C3H8O calculations for specific enthalpy. The reason being that the constant pressure heat capacity is not available in the tables provided from the appendix that was given. So we are going to assume that constant pressure of heat capacity of isopropanol in liquid state at any temperature is 0.1599. Therefore, we can now calculate it. Moving on to the unit operation for energy balance. It's basically the same concept. It's generally the same concept from earlier on.
Hi everyone, my name is David, and today I would like to briefly explain to you how do we solve the piping layout problem. First, we have a reactive system. After making some assumptions, we want to find the mean velocity at the first place. Then we proceed to find the Reynolds number, then the friction factor, and the friction loss. And after getting the friction loss, we are able to calculate and get our pressure drop. And here we want to solve the second pipe, which is the propellant feed to the reactor. And we can use the same concept and the same method. First, we find the velocity. Second, we find the Reynolds number. Third, we find the friction factor. Fourth, we find the friction loss. And then we can get our pressure drop. So for our reactive system, piping number 3, we need to take note that it is not about a single component. It is a mixture of water and isopropyl alcohol. So when calculating the density and viscosity, we need to take into account that, which is to multiply the mass fraction with the original viscosity or density to get the new viscosity or density. So when it comes to non-reactive system, the complexity even increases because we have 3 components in one mixture, which is water, isopropyl alcohol, and benzene. We can also still apply the same method to get the pressure drop. And for non-reactive system piping number 7, you can see that this piping system only consists of one component, which is isopropyl alcohol purely. And you can see the pressure drop there. The negative sign indicates that P1 is greater than P2. And for non-reactive system piping number 7, you can see that this piping system only consists of one component, which is isopropyl alcohol purely. And you can see the pressure drop there. The negative sign indicates that P1 is greater than P2.
Moving on to the transportation strategy of main product, we have considered 3 main elements, which is pipe, pump, and tank. For the pipe, we have considered to use 100 meter schedule 40 stainless steel pipe with 1 inch size and is uninsulated because to let heat flow. Next, centrifugal pump is used with efficiency of 90% to provide a smooth flow of isopropyl alcohol. Meanwhile, for the storage tank, it has to be grounded and has floating roof tank. This is to avoid hazard associated with static discharge. The material of the storage tank is stainless steel, and this material can withstand the properties of the product. Some of the advantages using stainless steel tank are corrosion resistance, fire and heat resistance, sustainable and long-term value. Besides that, the area of the storage tank should be well ventilated and away from direct sunlight, as the product is flammable. The storage tank is assumed to be able to store 6,000 tons of isopropyl alcohol. The height of the tank is fixed to be 10 meter, while the inside diameter of storage tank is assumed to be 30 meter and outside diameter of 39 meter. This is to withstand the high pressure due to flowing fluid. To estimate the pump power, these are the assumptions used in the calculations. So this is the calculation to estimate the pump power of the piping system. After some calculation, the estimated power of the pump is 10.09 kW. In summary, this integrated design project focuses on the production of isopropyl alcohol from propylene gas and water. Through the application of mass balance, energy balance, and Bernoulli's equation, this has effectively showcased the symbolic relationship between principle of chemical engineering and fluid mechanics. Moreover, this integrated design approach holds promise for optimizing other fluid flow systems, potentially yielding substantial cost savings and enhancing sustainability across various sectors.